The machine is ready.
Interior
Let's go.
operator.
Ready.
So what are we waiting for?
The trolley.
Where is it?
It is currently contributing to another department.
Right.
And welcome to the deep dive.
Yeah.
I mean, you might have like $5 million worth of robotics on your shop floor right now, perfectly calibrated and completely ready to run.
Yeah, ready to go.
Right. But if they are just sitting idle because 3 different departments are currently hunting for the exact same $100 material trolley, your $1 million investment is completely subordinated to a piece of bent metal on casters.
It's just sitting there.
Exactly. So today we're taking a look at field note number 014, which is called "The Costliest Tool May Be the One Shared by Everyone."
It's a great piece.
It really is.
Yeah.
We're basically dismantling this illusion that the most expensive asset in your operation is automatically the one driving your throughput. Because by the end of this discussion, you're going to be equipped to recognize shared resource dependencies on your own floor, map the overlapping requirements, test practical changes to location and reservation, and ultimately make an evidence-based capacity decision before you just reflexively purchase another unit.
Because that's the reflex, right? Just buy another one.
Totally.
Yeah.
So let's jump right into this premise we're dissecting here. It challenges this really persistent cognitive bias we have in capital allocation.
Yeah, we definitely tend to focus all our analytical energy on the assets that carry the highest purchase value. I mean, it's natural.
Like the big shiny machines.
Exactly. But operational reality is governed by dependency, not acquisition cost.
Right.
So when we look at these modest, low-value shared resources, like an illustrative trolley or a specific calibration gauge or maybe a handheld scanner or a portable lifting device, we see that they can unexpectedly mutate into these severe operational constraints.
Oh, absolutely. They just choke the flow.
Yeah.
And not because they're mechanically complex, right?
No, not at all. It's because they are the physical intersection point for multiple overlapping process requirements.
So the trolley is inexpensive.
Yes.
And several expensive processes are waiting for it.
Yes.
That feels like a surprisingly senior role for a trolley.
It really dictates the pace of the entire floor, honestly. And to understand how this happens, we really have to look at Eli Goldratt's theory of constraints.
Oh, yeah, from the semestic source.
Right. The semestic source explores this in a lot of detail. In production environments, we frequently misuse the terms bottleneck and constraint interchangeably, but they are fundamentally different mechanisms.
Yeah, people use them like they're synonyms, but they're not.
Exactly. A constraint is really anything that prevents the system from achieving a higher goal. So that could be like a broad policy or a mandatory quality inspection rule, or even a market factor where demand simply doesn't exist.
Right, like you just can't sell any more widgets.
Exactly. But a bottleneck is a specific physical limitation inside the production process itself. Its capacity is equal to or less than the demand placed upon it.
Let's ground that distinction for a second.
Yeah.
Think of like a major highway, right?
Yeah.
A constraint might be the legal speed limit. It restricts throughput system-wide based on a policy. But the bottleneck is the lane closure at mile marker 12.
That's a really good way to visualize it.
Right. The physical geometry of the road simply cannot accommodate the volume of cars trying to pass through that specific coordinate at that specific time.
A highly accurate translation of the mechanics, really. And what makes the shared resource so insidious is that the suspected bottleneck on a shop floor is usually the noisiest machine, right?
Always.
It's the one with the largest queue of work in progress or the one with the highest historical downtime. So management focuses all their lean initiatives on that machine.
They just swarm it with consultants.
Right. Yet the single shared calibration gauge acts as a phantom bottleneck. I mean, its capacity isn't limited by its cycle. Time reading a gauge takes seconds.
Literally seconds.
Its capacity is exhausted purely by conflicting demand schedules. It sets the pace of everything else, and it does so completely quietly.
The quiet nature of this bottleneck is what fascinates me, especially when we cross-reference it with the Nokia source, which pulls in data from Sandvik Coromant.
Oh yeah, the Sandvik Coromant data is staggering.
It really is. The numbers here describe an absolute paradox of inventory. They track that workers lose up to 20% of their productivity strictly searching for missing tools.
20%, that is massive.
Massive. If an operator is hunting for a shared scanner for even a fraction of their shift, Those lost minutes, they compound into weeks of lost throughput annually.
Easily.
But the paradox is that Sandy-Corman also calculates that 60% of tool stock in machine shops is never actually used.
60% just sitting there.
Right. So if we have 60% idle inventory, why are we still waiting for a trolley?
Well, the mechanics of that paradox are really rooted in a behavioral response to unreliability.
What do you mean?
We can call it the security blanket phenomenon. Because when a critical shared tool goes missing and $1 million cell goes down, the financial pain is immediate.
Oh, yeah. People notice that immediately.
Right. So the natural management response to that pain is to flood the system with redundancy. They just authorize the purchase of duplicate backup stock.
Panic buying.
Exactly. But they execute this purchase without addressing the underlying mechanics of why the original tool vanished in the first place, which is, anonymity, poor location discipline, and uncoordinated demand.
So they're just throwing capital at a coordination problem.
That's exactly it.
So the active tools, they still migrate into personal toolboxes or get stranded in distant departments, while the brand new, expensive backups just sit idle in a central crib.
Because the operators don't even know they exist?
Right, or the friction of walking across the plant to requisition them is just too high.
Yeah.
You end up, drowning in physical assets while simultaneously starving for them on the line.
Which brings us to the real diagnostic challenge here. Where does this massive inefficiency actually manifest in the data?
Right, because it's invisible.
It almost never appears under its true name. You will rarely, if ever, see a shift report explicitly cite a trolley problem.
Never.
The loss masks itself. It will register as machine waiting, or a material movement delay, inspection delay, an extended changeover, work resequencing, or just generic operator searching.
Just general downtime category.
Right. And we should clarify that these are possible manifestations requiring local verification. But the central observation we must establish is this. The report may record where the waiting occurred without identifying the object connecting the weights.
Yes. The reporting system tracks the victim, not the culprit.
Well said.
I mean, the OEE dashboard lights up and says, Machine B is down for material starvation. It doesn't tell you that Machine B is starved because the material handler is currently wandering through 3 different zones looking for the specific lifting device that Department A borrowed and never returned.
It's invisible waste.
Completely invisible. And the iFactory AI data isolates this invisibility brilliantly, specifically looking at MTTR in spinning and weaving mills.
Mean time to repair, yeah.
Right. Their analysis reveals that 15 to 25% of total MTTR is strictly parts hunting time.
Wow.
It is not repair time. The mechanical breakdown of the loom is only a fraction of the downtime event.
Let's actually dissect that, like a theoretical 30-minute loom repair, just to see how those mechanics play out on the floor.
Yeah, let's walk through it.
So an alarm triggers. The technician arrives at the loom. Diagnosing the issue, like identifying that a specific gear needs adjusting, takes perhaps 3 to 8 minutes.
Pretty standard.
Right. But then the technician has to retrieve the specialized knotting tool or, track down the calibration setting sheet.
And because those resources are shared across 50 looms.
Exactly. The technician spends 15 to 40 minutes walking, checking adjacent stations, and just hunting.
Just walking around asking, hey, have you seen the thing?
Yeah. And the actual wrench time, putting the tool to the metal and fixing the gear, is only 10 to 20 minutes.
So the delay entirely surrounds the repair. It does not constitute the repair itself.
Right. The technical intervention is bracketed by logistical failure.
And this is where, drawing on practical floor experience, we see a classic, just flawed intervention from management.
Oh, absolutely.
When they look at the dashboard and see MTTR trending upward, their immediate reflex is to question the competence of the maintenance team.
Right. They think the techs are the problem.
The directive becomes, our technicians are too slow, we need to upskill them, or we need to apply more pressure to hit repair targets.
But if you look at the iFactory mechanics, you cannot outskill a search party.
Right.
If the physical act of turning the wrench is already optimized at 10 minutes, sending that technician to advanced mechanical training does absolutely zero to mitigate the 40 minutes they spend looking for the shared gauge.
It's completely useless. The operative constraint in that scenario is readiness, not competence.
Exactly. It is the availability of spares, tools, and instructions.
So if we accept that this loss is hiding in plain sight, masking itself as inflated MTTR or machine downtime, the intervention requires exposing the true dependency. We have to map the users and the demand, before anyone is permitted to sign a purchase order for another unit.
And mapping the dependency is where this gets incredibly practical, because for every process that relies on this shared asset, we need to capture the who, what, when, and where.
The basics.
Right. Who needs the resource? At which process stage? How does that need actually become known to the system?
Like, does a light go on? Does someone yell?
Yeah, exactly. And where is the resource collected? Where is it used? And where is it returned? And critically, what specifically is forced into a waiting state when it is unavailable?
And we really have to emphasize the methodology for this mapping. The sources heavily imply that this investigation must utilize simple, locally understood terms.
Simple is key.
You cannot prescribe a complex digital booking platform or like an enterprise software module at this early stage.
Yeah.
I mean, operators won't fill out a 10-page form just to use a scanner.
No, they definitely won't. The friction of the mapping tool cannot exceed the friction of the problem. A basic observation sheet, a paper record on a clipboard, or a localized magnetic board is entirely sufficient to render the shared demand visible.
We have to protect the practical usability of the floor here. If you mandate that an operator must log into a terminal and fill out a digital requisition form with 7 drop-down menus just to use a handheld scanner for 2 minutes.
They'll just find a workaround.
Yeah, or worse, they will hoard the scanner, which ties directly into a principle from the instant systems source that I think completely nails the psychology of the shop floor. The absorbed, not stolen principle.
I love this principle. It completely reframes the narrative of missing assets. Tools rarely evaporate due to malicious theft. They get absorbed into personal workflows due to the anonymity of the shared system.
Right. Think about a technician who needs a specialized torque wrench for a quick adjustment.
Okay.
They walk to the central crib, grab it, and bring it to the machine. The adjustment takes 5 minutes, but right as they finish, a priority 1 alarm goes off on the other side of the plant.
So they just drop it.
They drop the wrench in the bottom drawer of their roll cart and sprint to the emergency. 3 days later, that shared torque wrench is permanently living under a pile of rags in their personal toolbox.
It just lives there now.
Yeah. They didn't steal upon it. They absorbed it because the system provided no mechanism to tie the item to their identity, and returning it offered no immediate value.
Because there is no visible chain of custody, the loss ceases to be anyone's individual responsibility and immediately becomes a systemic cost.
Exactly.
And we should note, the objective of the manual mapping phase is not to build a granular second-by-second utilization model to punish that technician.
No, definitely not.
The objective is simply to identify the primary users and the flow paths. Once we identify the nodes in this network, we have to map the specific timing of the overlaps.
Right. We need to map time and collision.
Right.
When is the request initiated? When is the resource actually received? When is it returned? Are requests overlapping? And if someone holds onto the tool longer than expected, what is the operational reason for that extended use?
The ShopLogic source provides excellent framing for this, particularly in the context of cellular manufacturing.
Yeah, how does that play out in a cell?
Well, in a compact production cell, work flows sequentially or semi-sequentially through a cluster of interdependent equipment. The ultimate constraint is the continuous flow of the product, not the maximum speed of any individual machine. So if Station C halts because it lacks a shared measurement tool, that downtime event propagates in both directions.
Right, it's like a multi-stage prep line in a commercial kitchen sharing a single specialized frying pan.
Great analogy.
If the chef at the stove, which is Station C, is waiting for the pan, they stop cooking. The prep cook chopping vegetables at Station B suddenly has nowhere to put their finished ingredients, so they become blocked.
Exactly, they're blocked.
Meanwhile, the expediter waiting to plate the dish at Station D has nothing coming down the line, so they become starved. One missing pan cascades into a complete system freeze.
The cascading effect is precisely why OEE categorization must be highly specific. Overall equipment effectiveness software shouldn't merely categorize Station B and Station D as machine down.
Right, because the machine isn't actually broken.
It must dynamically tag those events as blocked by downstream constraint or starved by upstream delay, pointing back to the shared tool at Station C.
That makes total sense.
However, there is a strict methodological rule we must enforce during this manual mapping phase.
What's the rule?
The aim is to understand whether requests collide, not to create false precision from incomplete observation. We cannot mathematically invent time windows in a spreadsheet.
Oh yeah, you can't just guess.
If evidence is absent, the scale and timing of shared demand must be observed locally.
You actually have to go out on the floor and watch.
Yeah.
Let's illustrate how scheduling, rather than scarcity, creates these collisions.
Okay.
Imagine 4 distinct machining processes arranged in a square, all sharing a single, highly sensitive calibration gauge in the center.
Right.
If process 1 finishes its cycle at 10 euro AM and needs the gauge, and process 3 finishes its cycle at exactly 10:00 AM and also needs the gauge, the tool is a bottleneck.
Yes.
But it is a bottleneck engineered purely by overlapping cycle times. If process 3 was staggered to finish at 10:15 AM, the constraint vanishes without spending a single dollar on a second gauge.
That's a perfect example. The collision is temporal, not quantitative. But temporal overlap is only one dimension of the dependency.
What's the other dimension?
The physical distance the tool must travel introduces an entirely different vector of waste. We have to map the journey.
And this brings up the most glaring disconnect between the facility blueprint and the physical reality of the shop floor. We need to examine the assigned home location, the actual return locations, the collection routes, the handoffs between shifts, and how visible the tool is to the current and next user.
Let's do a quick observational exchange here. Does the resource have a fixed home?
On the layout, yes.
And physically?
It appears to work remotely.
Right.
And, that is the daily reality for anyone running a shift. The tool has a beautiful labeled silhouette on a pegboard in a crib located 300 yards away from where the actual work happens.
Which is completely impractical. The ShopLogix data categorizes this under the umbrella of walking waste, an asset that technically exists on the ledger but forces a highly skilled operator to walk 500 steps across a manufacturing cell to retrieve it, exerts a massive silent drag on OEE.
It's huge. The physical layout often forces the operator into a behavioral double bind.
A double bind.
Yeah. The system demands high throughput and adherence to tight cycle times. That's what they're measured on. Simultaneously, the system demands that the operator return the shared scanner to a central charging cradle on the opposite side of the facility. The operator cannot fulfill both mandates.
So they prioritize throughput.
Exactly. They leave the scanner sitting on the casing of machine A because making a 10-minute round trip to put it away feels like actively sabotaging their own production quota.
And we cannot frame that decision as employee laziness.
No. It is a system design flaw. The system forces the human to choose between keeping the line running and maintaining tool organization.
So having mapped the users, the timing, and the physical journey, we reach a critical transition point. We move from observation to intervention. We begin testing location and reservation changes.
And these must be low-cost experiments, right? We aren't buying anything yet. We are changing the physical flow.
Right, simple changes.
This could mean establishing a fixed, visually identified home position on the floor using floor tape and signage. Or it could mean completely relocating the tool nearer to the concentrated demand practicing point of use positioning, rather than clinging to where the architect drew the tool crib a decade ago.
The location change must be paired with a proportionate reservation method. If multiple processes require the tool, the coordination must be visible.
Like what kind of visible coordination?
This could involve a simple time slot board with dry erase markers at the point of use, a physical token indicating the current user, or establishing clearer collection and return ownership, like clear priority rules. For example, safety-critical inspections always preempt routine calibrations.
Right, but the friction of the reservation system cannot outweigh the value of the tool. If you implement a system that requires a manager's signature, a digital dual authentication login, and a 24-hour lead time just to use a portable lifting device, you will successfully eliminate the overlapping demand. But you will only achieve that by discouraging anyone from ever using the tool. It has to be frictionless.
Frictionless and, crucially, blame-free.
Oh, this is huge.
There is a cultural rule that must be rigidly maintained during these experiments. Avoid blame. When you map the demand and discover that the assembly department has been hoarding the shared trolley for 3 weeks, you cannot use that map as a weapon.
Right, because their operational need for that trolley is likely entirely legitimate and born out of previous unreliability.
Exactly. If you storm into the assembly department demanding to know who has the trolley, you immediately trigger a defensive reaction.
Oh, the tool will vanish deeper into the shadows. The operators will protect their resources.
So the correct systemic question is not who has the trolley. The correct question is, why does a resource needed by several interdependent processes rely entirely on everyone remembering where it was left?
Right. You're fixing a process dependency, not prosecuting a behavioral failing. So we run these manual tests. We tape off a square on the floor, we put up a whiteboard, we establish our priority rules. That works beautifully for one trolley or one gauge. But what happens when the operation scales?
When it gets too big.
Right. What happens when you have a facility with 4,000 shared assets and the manual methods hit their absolute administrative ceiling?
Well, that is the threshold where we look to scale with technology. Once the manual flow is thoroughly understood and corrected, facilities can deploy technology to automate accountability.
But it has to do so without adding administrative burden to the operator.
Exactly.
Hmm.
And we look to the instant systems, the Aricheng RFID data, and the Nokia sources for these mechanisms.
Let's break down the mechanics of the instant systems smart cabinets, specifically the weight cell technology, because this is an elegant solution to the friction problem. How does this actually work on the floor without slowing the operator down?
The brilliance of the weight cell mechanism lies in its passive data collection. The cabinet is fitted with high-precision load sensors beneath every shelf or bin. When an operator authenticates, perhaps by swiping their standard employee badge to unlock the door, the system establishes their identity. The operator reaches in and takes a specific wrench. They do not scan a barcode. They do not press a button on a screen. They simply close the door.
And the system does the math in the background.
Precisely. The load sensors calculate the delta in mass. It knows that bin 4 just became exactly 450 grams lighter. Because the system's database knows the precise tare weight of that specific wrench is 450 grams, it automatically registers the tool as withdrawn.
And it links that withdrawal to the badge swipe of the specific operator.
Exactly. It eliminates anonymity instantly, achieving total accountability as a byproduct of normal use.
That completely neutralizes the absorbed, not stolen phenomena. If the tool ends up in their personal toolbox, the system knows exactly who put it there.
Yes, it does.
But a cabinet only secures the tool at its origin.
What about mapping the journey of the trolley or the lifting device as it moves across a massive facility? That brings us to the Aricheng RFID data, which outlines the physics of radio frequency tracking. RFID deployment requires a nuanced understanding of frequency mechanics based on the environment. The data highlights UHF ultra-high frequency for long-range applications like broad tool cribs or warehouse environments.
Right.
UHF waves can travel several meters, allowing a single reader to sweep a large area.
But UHF has physical limitations on a shop floor, right?
Yeah.
I mean, if you blast UHF waves into a cabinet full of metal shelving and steel tools, the radio waves bounce and scatter.
Yeah.
You get false reads.
That is exactly the issue. The metal reflects the electromagnetic energy. That is why for localized, highly precise tracking like inside a smart tool drawer, the system must utilize HF, high frequency.
Oh, okay.
HF has a much shorter read range, usually just centimeters. It relies on magnetic coupling rather than backscatter, which means it can read tags densely packed near metal without the signal bouncing erratically.
And for shared tools physically operating on the floor tools, exposed to extreme vibration, synthetic oils, or high heat, the tags themselves must be ruggedized, encased in industrial polymers to protect the antenna and microchip.
And the Nokia source pushes this even further into broader positional technologies. They detail HAIP, high accuracy indoor positioning.
What does that use?
This uses Bluetooth low-energy arrays to map the intricate real-time routes of human operators and AMRs.
Autonomous mobile robots.
Right. They also touch on visual position systems, which use AI-driven video feeds to track the physical footprint of assets without needing to stick an RFID tag on them at all.
Those technologies offer incredible visibility, but they introduce a severe strategic risk if applied prematurely.
Yes, they do.
And this is the warning for anyone listening who is currently opening a new tab to solicit quotes from RFID vendors. Technology solidifies a good process. It does not invent one.
That is crucial.
If you buy a massive multi-million-dollar AI visual positioning system to track a trolley because you haven't done the basic manual mapping to figure out why 4 departments need that trolley at the exact same time, you're wasting capital.
Automating a broken, highly conflicted process merely provides highly accurate, real-time data about how badly your system is failing. The physical flow must be rationalized first.
Which brings us to the ultimate outcome of this exercise.
Yeah.
You've mapped the users. You've mapped the collisions. You've tested new locations, maybe implemented weight cells or localized tracking. All the data is in front of you.
Right. So what now?
How does a manager make the final evidence-based capacity decision?
The decision to purchase another unit is justified only when observation confirms that the constraint persists despite optimized coordination.
So what are the criteria?
The criteria are strict. If demand still overlaps materially even after schedules are staggered, if travel time remains a severe drag on OEE because the physical footprint of the facility makes point-of-use storage impossible, or if that single resource demonstrably continues to throttle overall flow despite perfect, frictionless reservation.
It maps perfectly onto the semantic sources breakdown of the theory of constraints loop. Identify, exploit, subordinate, elevate.
We can trace our entire discussion through that loop, actually. First, we identified the constraint, realizing the trolley, not the milling machine, was throttling production. Second, we exploited the constraint. This means maximizing the use of the current tool without spending capital. We did this by mapping the journey, removing the walking waste, and testing better locations so the tool is always in use, not in transit.
Third, we subordinated everything else. We staggered the process schedule so that machine A and machine C aren't demanding the gauge at the exact same moment. We aligned the rhythm of the multi-million-dollar plant to the availability of the shared resource.
And only after exhausting those 3 steps do we reach the fourth: elevate. Elevating the constraint means spending capital to add capacity. Buying a second trolley or a second scanner is elevation.
If you jump straight to elevation, if you just buy the second tool without exploiting and subordinating the first one, the consequence is deeply painful.
It's a mess.
The factory acquires a second shared tool, drops it into a system with zero location discipline and total anonymity, and immediately begins a much more ambitious, facility-wide search operation for both of them. You haven't solved the bottleneck. You've just doubled your inventory of missing items.
A capacity decision not rooted in evidence simply scales the dysfunction.
So, to summarize the mission we've mapped out for you today, the next time you see machine down, look beyond the purchase value of the asset. Distinguish what a tool costs from how heavily the operation depends on it.
Map the users and demand using simple, low-friction observation.
Track the physical journey and the overlapping schedules to see where time is bleeding out. Test basic physical solutions like fixed home locations without resorting to blame.
And let the evidence of the floor, not the frustration of a single shift, drive your decision to buy more capacity.
As we close, I want to pivot this logic from physical assets to organizational design. Consider the invisible shared resources operating in your facility right now.
That's an interesting thought.
We have focused on trolleys, gauges, and scanners. But what happens when the shared resource is human?
Right, a person.
What if the constraint is a highly specialized maintenance technician whose expertise is required by every department? What if the constraint is a centralized IT security approval process that every new initiative must pass through?
If you apply this exact same mapping logic, tracing the overlaps, the walking waste, the invisible demand to human shared resources and administrative workflows, how much cascading delay and invisible search time would you uncover?
The costliest tool in your operation might just be a person or a process that everyone is quietly waiting for. Thank you for joining us on this deep dive. Take this mapping logic, test it on your floor, and start hunting for your invisible constraints. See you next time.